Alrighty, folks. Today we're talking about section 6.1 in Algebra 2 and Trig, which deal with roots and radical expressions. The first thing we want to take a look at is the parts of a radical. Hello, everyone! And yeah, so we're talking about radicals. Ladies and gentlemen, just real quick, I'm going to erase this and redo it for you. The parts of a radical. Well, the symbol itself, that is the radical. This guy is actually called the radical. Right? Like Mr. Cohen was a radical in the 60s. Now, inside the value of the radical, you'll have a number there. This number, call it n, is known as the index of the radical. And the number that's inside of here, whatever number you have, this is called your radicand. Okay? So those are the three parts of the radical. Now, the ones that you're used to are what we call square roots. Now, a square root is a radical whose index is 2. So there's really a 2 there. But the only radical that can have an invisible radical is the square root. If you don't see a number there, see how the 2 disappeared? If you don't see a number there, then you know that's a 2. Okay? Now, the index tells me how many times I have to multiply a number by itself to get the radicand. So what number times itself 2 times is 25? 5. In the next problem, this says what number times itself 3 times is 27. Well, let's see. I think it's 1. 1 times 1 times 1. Oh, no, that's 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Oh, the answer is 3. Look at this one. This is a humdinger right here. What number times itself 5 times is 32? Peace to you. Peace to you, young man in the back. Oh, you're saying 2. 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times another 2 is 32. So 32, that's correct, okay? So the radical tells me...
There's no boot camp today, apparently.
Okay, and as we said, what number times itself 5 times is 32?
2.
2, that's right. Okay, ladies and gentlemen, now, so that's how we work with radicals. We look at the index, and the index tells me how many times a number has to be multiplied by itself to get to the radicand, okay? Simple as that. Now let's look at some algebraic problems. If I want to simplify algebraic expressions, this says, this first example, I've got the square root of x squared, y to the 4th, and z to the 10th. Right? Now, I'm going to rewrite this square root in this fashion. I'm going to expand out all the x's, y's, and z's. X squared means x times x. Y to the 4th means y times y times y times y. And z to the 10th means z times 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 z. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This looks like AJ in the middle of class. All right, so I've got 2 x's, 4 y's, and 10 z's inside this radical. Well, again, since I'm looking for the square root, I'm looking for pairs of the same number, right? Okay, so some people like to write it out like this and then say, all right, the square root says you have to have 2 of the same thing for that thing to come out. Well, I've got 2 x's, right? So I've got a pair of x's since I'm looking for square root, so the x gets to come out. For the y's, I've got 4 y's. Well, how many pairs of y's? Oh, that's a pair of y's, so that y would come out. That's another pair of y's, that would come out, right? For the z's, a pair of z's come out, another pair of z's come out, another pair of z's come out, another pair of z's come out, and another pair of z's come out. So in total, I have 1 x that came out of the radical, y squared came out of the radical, and z to the 5th comes out of the radical. All right? And so that is the square root of x squared, y to the 4th, 10 to the, z to the 10th. Now you might sit there and say, golly, do I have to do it this long, convoluted way every time? Well, there is a shortcut. If you take a look at this, did we say the index of this radical is? It's a 2. Well, let's take a look at this. How could I have worked with this exponent and this index? How could I put these together to get a final exponent of 1? Dividing. 2 divided by 2 is 1. Check it out. What's 4 divided by 2? 2. And what's 10 divided by 2? 5. So in short, if you want to do this, you can just divide the exponent by the index, and that'll tell you your answer. But now just hold your horses Because sometimes you might have a problem here. Take a look at this next one. If I've got the square root of x to the fourth, y to the fifth, z to the seventh, I know that I've got 4 x's in here, and 4 divided by 2 would be x squared. Now, for the y's, if I divide 5 by 2, I know I get 2, so y squared, but don't I have a remainder of 1? So, in other words, that remainder must remain inside this radical of square root. Similarly, z to the seventh, 7 divided by 2 is 3 with a remainder of 1, so that remaining z must stay inside the radical. Okay? And so that's your answer to that problem. Looking at the next radical, oof, I've got an index of 4. All right, and now on this doozy, I've got the fourth root of 16 x to the 8th, y to the 14th. Well, the first thing is 16. Let's try and break 16 down. Well, 16, using your factor tree, is 8 times 2. 2's done. 8 times 8 is 4 times 2. 2's done. 4 is 2 times 2. The 2's are done. So in total, 16 has 1, 2, 3, 4 2's in it. Can everybody see 4 2's? All right, so that's 4 root of 2 to the 4th, x to the 8th, and y to the 14th. Now, to simplify this, I divide this exponent by this index. 4 divided by 4 is 1. That's the same as 2 to the first. Because remember, I'm taking out groups of 4, aren't I? How many groups of 4 can I take out of 2 to the 4th? 1 group of 2, right? X to the 8th, I can take out 2 groups of x to the 4th. And out of y, I can take out 3 groups. But wouldn't there be 2 left over? Wouldn't there be 2 y's that didn't? Because 14 divided by 4 is 3. But I have a remainder of 2 y's that didn't group up. Now, this is not the correct answer. Why is it not correct answer? This is the part that a lot of people forget. Ladies and gentlemen, if I start with the fourth root, you have to put a 4 in that index there. Don't forget that. Okay? Okay, now the next one's to the cube root of 81 x to the 7th, y to the 9th, z to the 20th. That's a good point. That's a good point, young man in the back. You guys try and do this one on your own. Put those in your notes, and we'll go over that answer mañana. All right. Now, ladies and gentlemen, the next part I want to talk about is the difference of types of indices. Folks, there are 2 types of radicals that we need to focus on. We have even radicals, like square root, 4th root, 6th root, and we have odd radicals, all right, where we have like cube root, 5th root, 7th root, all right? There are some important ideas that we need to focus on here. When you have an even root, okay, even radicals. With even radicals, here are the 2 things you need to be careful of. First and foremost, number 1, and we've talked about this, you can't have negative radicands. Okay? We know that the square root of -4 is not allowed in the real world. Okay? So in other words, the 4th root of -25 also not allowed. Okay? The second thing you have to be careful of. Okay? The second thing that you have to be careful of when you're working with even radicals is this. Even radicals can technically produce 2 answers, a positive number and a negative number. Like, for example, if I said to you, hey, what number if you square root 25, what number times itself could be 25? It could be positive 5 or negative 5, right? Well, in math, we say if I just see this, square root of 25 for even radicals, right? There are 2 versions. This is actually the positive root. If I just see a plain old square root, that's implied that that's a positive. If I want the negative version, I'll do that. Right? The answer to this one is 5, whereas the answer to this one is -5. Okay? All right? So with even radicals, we can't have negative numbers inside the radical, and you can sometimes have a positive answer and a negative answer. Be careful. If you see no symbol here, then we just want the positive answer. If you see a negative sign, then we want the negative answer. Now with odd radicals, well, if you look at, say, the cube root of -8, Is it possible to multiply a number times itself 3 times to get a negative 8? Golly, yeah. Negative 2. If you multiply negative 2 times negative 2 times negative 2, don't you get negative 8? So what is the cube root of negative 8? It's negative 2, right? So with odd radicals, you're allowed to have negatives inside of there. You can get an answer, okay? If you see a negative in front of the inside of an odd radical, you must always pull out the negative sign. Okay? So if you have the cube root of, say, negative, and now watch this, what I'm going to do here. I'm going to do the cube root of negative 54. Well, the negative I know can come out because 3 negatives make a negative. Now 54, is he cube rootable? 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. No. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. Oh, past 54. That's not it. Oh, but wait a minute. Maybe we could do the same thing we used to do with square roots. You just, let's see here. Isn't 54, if I did a factor tree of 54, would you agree that's, let's see here, 9 times 6, which is 3 times 3, which is, and 3 times 2. So, would you agree, since I'm looking for groups of 3, don't I have 3 3s that could come out? So that would be negative 3, and then cube root of 2. See how I got that? Yeah? And that's how we simplify that radical. Okay? All right. I think that's it for today. Talk to you later.